This is page 13 of the scheduling notes. New section, section 5, is non-preemptive schedulers. And it's not actually plural because we're only going to look at one technique. There's the text reference 7.3. So with non-preemptive schedulers, it's what we saw at the start of the scheduling section, the bare metal, the super loop. So your tasks are really just functions that run to completion, and then the next function is chosen to run. So you're not performing context switches, you're not switching frequently between the functions or the tasks, and so it minimizes scheduler overhead. So there are no context switches, and that's going to have the effect of minimizes the overhead of the scheduling. On the other hand, it's very inflexible, as we talked about. Can't react to events, or at least not quickly. And so the technique is called timeline scheduling, otherwise known as the super loop. And the tasks execute in a fixed order, and this order is determined at compile time or offline. So the schedule is created offline at compile time. When stuff happens at compile time versus at runtime, that's called static sometimes, and if it's happening at runtime, it's called dynamic or offline and online, they're different terms. Okay, so let's look at an example. Our task set is composed of 3 tasks, and we're going to list the period, and just until you get used to the terminology, I'll just add that label. So we got T and C. C, as you hopefully remember, is worst case execution time, and also remember that the assumption is that DI equals the period. And we've got task 1, task 2, task 3. And let's just say that the period for task 1 is 18, and the worst case execution time is 8. So it's going to keep the processor pretty busy. It's got a utilization of 8 over 18, which is almost 50%. Task 2 is a period of 30, worst case execution time of 10, so utilization of 33%. And task 3 has a period of 45 and worst case execution time of 10. So before we schedule this thing, we should see if it's actually going to be feasible. So step 1 is the processor utilization less than or equal to 1. If it's not going to be feasible to fit everything onto the processor, or we're going to start missing deadlines. So let's calculate U. U is equal to the sum, if you recall, of C over T. So let's write that out. The sum I equals 1 to N of Ci over Ti. So that's going to be equal to 8 over 18 plus 10 over 30 plus 10 over 45, which equals 1. So there, 100% processor utilization. That's not sufficient to guarantee schedulability, but it is a necessary condition. So we might be able to schedule it. Step 2 is to determine the schedule length. How could we figure that out so that we get through all the different combinations of these different periods here? What we want is the least common multiple of the periods of each of the tasks. Least common multiple. So sometimes in class I'll ask what people think is the least common multiple, and somebody can eyeball it and say 90, which is the answer. 18 happens to go into 90 5 times, and I chose it because it worked out nicely. Okay, I'm going to continue this on the next page.